Lakshmi Prasanna, Assistant Professor, Department of ECE, Institute of Aeronautical Engineering. In this session, we will discuss about the operation of 8086 microprocessor in the minimum mode with the help of timing diagrams. So here, in order to know the operation of 8086 in the minimum mode, first we have to know how the architecture of 8086 will be when it is operating in the minimum mode. Then the operation of any architecture we will discuss with the help of timing diagrams. Now, so as we have discussed in the features, 8086 microprocessor can be operated in two modes. One is minimum mode and another one is maximum mode. Here, 8086 microprocessor general architecture is different. We have discussed that architecture of 8086 microprocessor in the previous sessions, that is the general architecture. Now we are discussing about 8086 microprocessor when it is operating in the minimum mode. So as 8086 microprocessor supports two modes of operation. What are the two modes means? One is minimum mode, another one is maximum mode. Now, so here, what is meant by maximum mode? Maximum mode is also called multiprocessor mode. Why? Because it is suitable for a system having number of processors. That means with 8086, we will have another processors also. That is why maximum mode is also called multiprocessor mode. Multiprocessor mode. Okay. So when this 8086 microprocessor is operating in the maximum mode, that means this maximum mode, it is suitable for a system having number of processors. That is why in the architecture of 8086 microprocessor, when it is operating in the maximum mode, since it consists of number of processors, in order to handle all that processors, we will have one extra block which is called bus controller block, and in that bus controller block only all the control signals will be connected. They will not be present within 8086 because it will be having more number of processors. And another mode of operation is minimum mode. So minimum mode is called uniprocessor mode because it is suitable for a system having only single processor. So minimum mode means it is uniprocessor mode. It is uniprocessor mode or single processor mode. Okay. So here minimum mode means it is suitable for a system having single processor. So if we observe the architecture of 8086 microprocessor, when it is operating in the minimum mode, we will have only one processor, that is 8086 only. No other processors will be there. Only one 8086 microprocessor will be there. And also all the control signals will be present within 8086 microprocessor itself. That is the major difference between this maximum mode and minimum mode. And in order to operate 8086 microprocessor in the minimum mode or maximum mode, we have one important pin which is called minimum and maximum mode pin. So that pin function and all we have discussed in the pin configuration of 8086 microprocessor. So what is that pin means here? MN/MX bar. Okay. So this MN represents minimum mode and this MX bar represents maximum mode. When this MN by MX bar pin, if it is made equal to 1, it will be operating in the minimum mode. If the signal is made as 0, it will be operating in the maximum mode. And so whereas in the maximum mode operation, we will not have bus controller block. We will have bus controller block. Whereas in the minimum mode, we will not have any bus controller block. Now, so coming to here, this is the architecture of 8086 microprocessor when it is operating in the minimum mode. So here we have different components like 8086 microprocessor, and here clock generator, and we have here demux, demultiplexer, and this is CS logic, which is nothing but chip selection logic, and here these are the latches, and here we can find transceivers, and next components are memories and IO devices. So all these are different components that are available in the architecture of 8086 microprocessor when it is operating in the minimum mode. Now, we will go in detail about each component. First, let us have the overview about this architecture. What are all the signals available? What is the function of that signal? Okay. Now, so here we are discussing about the minimum mode operation. So, we have one important pin which is Mn by Mx bar. So, when it is operating in the minimum mode, this Mn by Mx bar, so this Mn represents minimum, it is active low signal. So, in order to operate the processor in the minimum mode, you have to connect this Mn by Mx bar signal to VCC. Then only the minimum mode operation will be performed. Now, so this is the main thing to operate microprocessor in the minimum mode. And we have studied that this minimum mode operation is called uniprocessor mode, because in the minimum mode operation, it is suitable for a system having single processor. So if we observe this architecture also, we have single processor, that is only one 8086 microprocessor is there. Okay, no other processors here. So since only one 8086 microprocessor is there, all the control signals will be present within the block only. Okay. So for example, if you see 8086 here, the control signals like ready signal, memory and IO, and read, write, bus high enable, address latch enable, this is data enable, data transmit and receive. Okay, so reset, clock, all these are the control signals. If it is operating in the minimum mode, all these control signals will be present within 8086 microprocessor only. Now, and here we have clock generator. Okay, so this clock generator will produce the clock frequency for 8086 microprocessor. So based on the versions, 8086 microprocessor can be operating in different frequencies. Like for some processors, 8086 based on the version, it can be operated at 5 MHz or 8 MHz or 10 MHz. So that frequency to 8086 microprocessor will be given by this clock generator only. So there are number of oscillators that will be producing this clock frequency. Like we have LC oscillator, RC oscillator, okay, Colpitts oscillator. There are different oscillators that will produce the frequency. But among all the oscillators, especially crystal oscillator is preferred in order to produce the clock frequency. Why? Because only crystal oscillator means out of all the oscillators, this crystal oscillator is having high stability. This crystal oscillator is having high stability. So that is why out of all the oscillators, this is preferred to produce the clock frequency. And next one is here, demux. Okay, so this is one important component. So by using this component only, the read and write operations from the memory or from the IO devices will be decided. Okay. So here we have memory and IO, read and write signals. But here at the output of this demultiplexer, we have the combinations like 4, that is memory read and memory write, and also IO read and IO write. And the next block is here latches. Okay. So here already in the previous session we have discussed about what is meant by latch, and generally the latches are nothing but flip-flops here. We prefer generally D flip-flops, and we have also discussed how the D flip-flop will be working based on the clock input in the previous session. Based on that concept, here these latches will be operated by a control signal called ALE. ALE represents address latch enable. So based on this address latch enable only, the latches will be operated. So here generally in 8086 microprocessor, we know that there are multiplexed address and data lines and also multiplexed address and status lines. If this A latches are used, from this address data multiplex lines, the latches are going to separate the address. Okay, latches will separate the address only from address data multiplex lines. That is why the output of latches will be only address lines. Now, and we also have one more important component called here transceivers. Transceivers are also called data amplifiers. Okay, so here these transceivers will be operated by or controlled by the two signals called DT by R bar, that is data transmit and receive, and DEN, that is data enable. So the transceivers will be controlled by these two control signals. So here the main purpose of these transceivers are to separate the data from address data multiplexer lines. So here if you see the output of transceivers, only data lines will be there. Okay, so latches are going to separate the address and the transceivers are used to separate the data. That is why these transceivers are also called data amplifiers. And next, so coming to the next important block, that is chip selection logic. So here the chip selection logic, generally it is used for selecting the address bank. So we have even address bank and odd address bank. So from which bank this memory should be selected will be decided by this chip selection logic. So this is CSE. That suffix E represents it is related to even address. And next one is CSO. Okay, so this O represents it is odd address. So these signals will be used for memory mapping. And next two components that are available are here memory. So here we have RAM and ROM. So RAM means random access memory. Okay, so random access memory means it can only random access memory means both reading and writing is possible. Okay, so that is why for this block the read signal and write signal, both the signals will be there. Okay, so because random access memory means both reading and writing, so the two signals will be there. So not only related to here memory, we also have here chip selection logic related to odd and even. Okay, so they will be coming from this. Since here it is RAM, these are the two signals that will be connected to here. And next memory is here ROM. Okay, so ROM, ROM. So ROM represents read only memory. That means by only reading is possible. So that is why here only read signal will be there. Here writing is also there, but here write signal will not be there. Only read signal will be connected. Read only memory. And along with that, we will also have here odd and even chip selection. And next one is here I/O. So this I/O can be any peripheral devices. If any microprocessor wants to read or write the information from this I/O devices, that is peripheral devices, it is possible with the help of this I/O read and I/O write signals. So for all these ICs, commonly we have this chip selection. So this is the overview of this block diagram, that is architecture when 8086 is operating in the minimum mode. Now we will go in detail about each component and the signals related to this block. Now, so one important point we have to remember when 8086 is operating in the minimum mode, we have to consider this MN, MX bar pin. Okay, so this MX bar you can also represent like this or just simply by taking the complement. Okay, so it represents that this is MX, MN represents minimum and MX represents maximum. Okay, so this minimum is active high signal and this maximum is active low signal. Now, so in order to operate 8086 microprocessor in the minimum mode, we have to make this MN by MX bar 1. Then only it will be operating in the minimum mode because it is active high signal. Now, so connecting this MN by MX bar pin to 1 is nothing but connecting this MN MX bar signal to VCC. Okay, so making this as 1 means it is possible if you connect that signal to VCC. And next one is single microprocessor. Why? Because in the minimum mode, it is called single microprocessor or uniprocessor. Okay, so why? Because it is operating in the minimum mode. And next, coming to here, the control signals. So if it is operating in the minimum mode, all the control signals will be available within 8086 microprocessor itself. Okay, so here in the block diagram we have seen different control signals are there, and main control signals are chip select, read, write. Okay, so in 8086 microprocessor in the minimum mode, all the control signals will be present within 8086 microprocessor itself. So here the control signals like ready is one of the control signal. So we have seen the function of all these signals while discussing the pin configuration of 8086 microprocessor. And another control signal is here M by IO bar, which represents memory and IO operation. And another control signal is RD bar, read. Next, we have also have another control signal, write. Next one is BHE, that is bus high enable. And the control signals here like ALE, address latch enable, and DEN, data enable, and DT by R bar. So data transmit and receive. So all these control signals will be within 8086 itself. Okay, so that is the main difference, how 8086 microprocessor is handling the control signals. These control signals will be within 8086 itself. Now, so here coming to the components that are present in the system, that is architecture, when it is operating in the minimum mode means here we have different components like latches, transceivers, clock generator, memory and IO devices, and chip selection logic. And we also have demugs. So all these are the important components that are available in the architecture of 8086 microprocessor when it is operating in the minimum mode. Now, So let us discuss about each component in detail. So coming to the first component, latches. Okay. So here, if we observe the block diagram, what we have seen, latches are there. So latches will be controlled by the signal which is provided by 8086 microprocessor. That signal is called ALE. Okay. So these latches are controlled by ALE signal. So ALE stands for address/enable. ALE stands for address/enable. Now, so coming to here, these latches, how it is going to operate means, if the ALE signal is 1, it will be carrying the address lines. That means the address data multiplexer lines are demultiplexed, and these latches will be producing the output as address lines. And when this ALE is 0, they will be acting as data lines. Okay. So mainly the purpose of this latches is to separate the address. Okay. So anyway, here the address bus width in 8086 microprocessor is 20 bit. So latches are used to separate this 20 address lines. And also, if we observe the block diagram of that 8086 microprocessor minimum mode, so totally the number of latches here, the number of latches available are here 3 latches. Okay. So all the latches are octal latches. So the latches are here octal latches. So why? Because here we have to use 3 latches means the size of address bus, here the size of address bus is 20 bit. Okay. So that is why compulsory we have to use 3 latches, octal latches. And coming to here, latches, we know they are nothing but D flip-flops, and we have discussed already the operation of D flip-flop by giving the clock signal. And next important component is transceivers. Okay. And here these transceivers will be controlled by another control signals that are available in 8086 microprocessor. Okay. So these transceivers are also called as data amplifiers. So why these transceivers are called data amplifiers means, these transceivers are used to separate the data lines from address data multiplex lines. So they are called data amplifiers. So the output of transceivers will be only data. So these transceivers, they are used to separate data from multiplex lines. Okay. So especially these transceivers will be controlled by control signals like, so DEN and also DT by R bar. Okay. So as we know here, what is the purpose of this DEN? DEN represents data enable. So this signal indicates whether a valid data is available on the data bus or not. And here this is DT by R bar. So data transmit and receive. So transmission means here writing and reception means reading. So these are the 2 important control signals that will be controlling these transceivers. And this is DEN bar, which represents valid data on the data bus. And next one is DT by R bar, direction of data from or to the processor. Okay, so all these things will be done by this transceivers. Okay, so especially if we observe the block diagram, the transceivers, number of transceivers, like how many number of latches required means we have used 3 latches, octal latches. Similarly here, how many number of transceivers required in this minimum mode operation means here 2 octal data buffers. Okay, so why we are using only 2 octal data buffers means here the size of data bus. So based on the size of data bus. Okay, so in 8086 microprocessor, the size of the data bus is 16-bit. That is why only 2 octal latches are used. That means 2 octal data buffers are used. Whereas here, if you go for the latches, 3 octal latches will be used because the size of the address bus is 20-bit. And the next components are here, clock generator. Okay, so this clock generator, the IC number is IC8284. So the clock frequency that will be produced to 8086 microprocessor, generally it may be 5 MHz or 8 MHz or 10 MHz. This will be the operating frequency. And here especially this clock generator is used to produce clock frequency from crystal oscillator. Crystal oscillator. Okay, so out of many oscillators, the clock frequency will be produced by this crystal oscillator. Why? Because it is having high stability. Okay, so this is the reason to produce the clock frequency, crystal oscillator is preferred. And here the clock generator other purpose is, that means you will also have clock signal connected to this clock generator block. Another important function of this clock signal is, it is also used to synchronize some external signals. It is also used to synchronize some external signals with system clock. Okay, so this is the main purpose of this clock generator block. And the next important component is here, memory and I/O devices. So the function of this memory and I/O devices, generally we have seen the block diagram when it is operating in the minimum mode. So we have 2 types of memories. The 2 types of memories are ROM and RAM. Okay, so ROM represents read-only memory, whereas RAM is random access memory. Generally, here in the ROM, the program will be stored. That is why ROM is also called as program memory. And in the RAM, data will be stored. That is why RAM is called data memory. Okay, so out of all these, we also have I/O devices here. Okay, so the main purpose of this I/O devices is to communicate with the microprocessor. So here this I/O devices to communicate with microprocessor. And next important block is here, chip selection logic. Okay, so this chip selection logic, especially it is used for selecting the even address or odd address, especially during memory mapping. Okay, so this chip selection logic, it is required for selecting memory or I/O. So based on the mapping. depending upon address mapping of a system. So this is the main purpose of this chip selection logic. So this chip selection logic will be connected to two memories, that is ROM and RAM, and also with the memory, IO device. And next important block is here demux. So this demultiplexer, what is the use means? Here it represents the transfer type. So the two important signals that are connected to this demux block in the architecture, it is M by IO and RD bar. So the combination of these two signals will says, and also D and bar, the combination of these three signals says the transfer type. Like if it is 001, the transfer type is read from the IO. If it is 010, write to the IO. If it is 101, read from the memory. If it is 110, write to the memory. So these are the three important signals that are connected to this demux block component. And next important thing, that is what about the architecture and its important components. Next, coming to the timing diagrams here, the operation of 8086 microprocessor can be discussed with the help of timing diagrams also. Here, with the help of read cycle and write cycle. Now here coming to this read cycle, anyway, we have to recall about the bus cycle. So bus cycle means it represents 4 T states. One bus cycle represents 4 T states. So what are the T states means? T1, T2, T3 and T4. So if you wanted to include wait states, TW, it is represented with that wait states can also be inserted before T4 state only. So here, in order to draw the timing diagrams for read cycle, first we have to consider the clock signal. Okay. So here the clock signal is nothing but complete one bus cycle here, which consists of T1, T2, T3 and T4. If we wanted to include wait states, we can include, but before T4 only we have to include. Okay. And the next thing we have to consider is ALE signal, address latch enable. So the main purpose of this address latch enable is here, when this signal is asserted, only address will be transmitted. As we have discussed this while learning about the bus cycle. So the address will be transferred only during T1, whereas the remaining time states, the ALE signal will be disabled. Okay. So if you see here ALE signal, this is active high signal. It is enabled only during T1. It is enabled only during T1. Okay. So whereas in the remaining time states, the address ALE signal will be tri-stated. And next signal is about address and status signals. So in the 8086 microprocessor, we have address data lines and also address status multiplexer lines. Now coming to this address status multiplexer lines, it is a combination of address and status. As we know, the address will be enabled only during T1 state, whereas in the remaining T states, that is T2, T3, TW and T4, the status information will be available. So that is why here at T1, the address information is sent available, whereas during T2, T3, TW and T4, only status information is available. And next is about address and data. So this is also the combination of address and data multiplexer lines. Okay. So here address and data multiplexer line means only during T1 the address information will be available. The address information will not be available in the remaining T states. Whereas here the data information will be available in the remaining T states. That means the bus will be reserved to carry the data information. So that is why Under T1 only you have address enabled, whereas under this T2, T3, TW and T4 you will have data signals. So if you observe, these two are the combination of multiplexer lines, but in both the cases only during T1 address information will be there. In the remaining time states, whether data information or status information will be available. And next signal is RD bar. So RD bar represents, this is active low signal. Okay. So here RD bar represents read signal. Wherever the data information is available, the data will be read. So generally where the data information is available here, data or status information during the time states T2, T3, TW and T4. So during these time states only the read signal will be enabled. So especially if you see this read signal, it is active low signal. So in order to say that the read operation is being performed during that time periods, you have to represent with the logic low only. That means with negative pulse. It should be represented with negative pulse only. Because this is active low signal, so you have to represent with a negative pulse in order to say that the read operation is performed. Okay. So wherever the data information is available, in that only it can be read or write. And next signal is DEN. So DEN represents data enable. So if the signal is enabled, it indicates whether a valid data is available on the data bus or not. Okay. So if we see here this DEN bar, okay, so it is also active low signal. So in order to say that a valid data is available on the data bus, you have to draw with the help of negative pulse only, because this is active low, you have to represent with negative pulse. Okay. So whether a valid data is available on the data bus or not means, generally the data will be available on the data bus only during the time cycles T2, T3, TW and T4. Okay. So that is why it will be enabled only between T2, T3, TW and T4. So in order to say that in this time cycles, a valid data information is available. And next signal is DT by R bar. Data transmit and receive. So here transmitting is the active high signal and R bar is here. So it represents it is active low signal. Okay. So as I told here, transmit means write operation. Receive means read operation. Okay. So since we are discussing here regarding the read cycle, we have to consider here read as receive signal. Okay. So here receiver is active low signal. So in order to say that the data is being received, we have to indicate with negative pulse only. We have to indicate with negative pulse only. Okay. So this is the read cycle timing diagram for minimum mode. Similarly, we have write cycle timing diagram for minimum mode. So write cycle means here we have to concentrate on write. Same procedure only, but coming to here DT by R bar signal. So T represents in this case also transmit. That means transmit means write, and receive represents read. Okay. Now, so since we are discussing about this write, we have to concentrate on a signal transmit. Okay. So here transmitter means it is active high signal. Now, so in order to draw the timing diagram for minimum mode under this write cycle, first we have to consider the clock signal. Okay. So clock signal here consists of one bus cycle. Here T1, T2, T3, TW and T4. There is no rule that we have to draw compulsory TW. If we want to draw, you can insert the TW before T4. If it is not necessary, simply we can draw the bus cycle representing T1, T2, T3 and T4 states only. So after considering the clock signal, next we have to draw the ALE signal. So ALE represents address latch enable. It is active high signal. And this address latch enable is used to separate the address lines. Okay. So the address information will be available only during T1. At the remaining time states, it is not available. So that is why, since it is active high, only during T1, in order to say that the address is sent, we have to indicate with a positive pulse. Only during T1. At the remaining time states, it is active low. And the next signal is about address status lines. So among these address status lines, address will be sent only during T1, whereas the status information will be available in the remaining time states. Now, the next signal is address data multiplex lines. So here, in this case also, in the address data multiplex lines, only during T1, the address information will be sent, whereas in the remaining time states, the bus will be reserved to carry the data. So if it is address status lines or address data multiplex lines, in both the cases, the address will be available only during T1 state. Whereas in the remaining time states, that is T2, T3, TW and T4, whether the status information or data information will be available. And next is, we are discussing about the write cycle timing diagram. So that is why we have to draw the write signal. So in the previous case, we have discussed about the read cycle timing diagram. That is why we have drawn the read timing diagram. But here, since it is write cycle, we have considered here the write timing diagram. So WR bar here, so it is indicated as active low signal. In order to say that the write operation is being performed, you should also represent by indicating with a negative pulse. Okay. So since the data is available here during the time states T2, T3, TW and T4, this write signal should be activated only during these time cycles. Because this is active low, so you have to indicate with a negative pulse. And next signal is DEN. So data enable. It indicates whether a valid data is available on the data bus or not. So generally among all the time states, the data information is available only during T2, T3, TW and T4. So that is why only those time states the signal will be active. Okay, active means this is active low signal. So we have to represent with a negative pulse in order to say that it is activated. And next signal is DT by R bar, data transmit and receive. So as we have discussed here, transmit means write operation and receive means read operation. So since we are discussing about write, we have to consider here the transmit section. So here the transmitter is active high signal. In order to say that the data is being transmitted, you have to indicate with the help of positive pulse because this is active high. So this is the positive pulse from the complete bus cycle T1 to T4. Now, coming to here, this is the bus request and bus grant timing diagram. So in this bus request and bus grant timing diagram, we have to consider the signals that are available in the 8086 microprocessor when it is operating in the minimum mode. Okay. So here, first the clock signal will be there and next comes here hold signal. Generally, the microprocessor will check at the end of each clock cycle. Okay. So this is one clock cycle. This is another clock cycle. This is the next one. At the end of each clock cycle, the microprocessor will check whether there is any hold signal enabled or not. Okay. So if the processor observes that the hold signal is enabled in the next, suppose in this clock cycle, if it observes the hold signal is enabled, in the next clock cycle, it is going to send the hold acknowledgement signal. Okay. After sending the hold acknowledgement signal, if the complete instruction is executed in the next bus cycle, this particular system bus will be hand over to the requested master. So this is what about the bus request and bus grant timing diagram. So especially this hold and hold acknowledgement pins will be doing that. Okay. So hold pin is checked at the end of each bus cycle. Okay. So if it observes that it is enabled, in the next bus cycle, in the next clock cycle, it is going to release this hold acknowledgement signal. Okay. So if it is active before T4, okay, before T4 means, so for example, if it represent it is T1, T2, T3 and T4. Okay. So if it is active before T4 or during T1 of the current cycle, what it will do means, the CPU gives, okay, so here the CPU is nothing but microprocessor. So the CPU is going to give the HLDA signal, that is hold acknowledgement, in next clock cycle. Okay. So if it observes that there is hold signal enabled, in the next cycle it is going to give the hold acknowledgement signal. It means microprocessor. So after doing this and for succeeding bus cycles, the bus will be given to another requesting master. Okay. So this is how the bus request and grant operation will be performed by using this hold and hold acknowledgement signals. So this is what about the operation of 8086 microprocessor in the minimum mode with the help of timing diagrams. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.